Yeah, as I was saying, we'll try to focus on the SQL query optimization piece today. So previously, we have discussed few of the SQL optimization topics, but this topic is going to be slightly different. We'll see how it is going to be different. So when we talk about SQL optimization, we have I normally categorize them into two broad buckets. So one, we at a very high level optimization. So this is where we have covered some of the topics in the past while covering Looker or Snowflake or related elements. So here is where we get to see the topics like maintaining proper indexes for all the tables in a database, what kind of database it is. Is it using row-based compression techniques or columnar-based compression techniques? They have different. We have discussed this in the past, and we have also talked about some concepts like data clustering, partitions, pruning, aggregate awareness features, and each SQL client, right, MySQL or SQL Server, they come up with a native query optimizer feature. So it's sort of just like how we have a performance analysis tab in Tableau. So each SQL client will also have something called as query optimizer. It will basically help you identify what kind of improvements that you can make. So we have discussed a little bit of all of these things in the past, and the interesting thing about these things are these topics are highly documented, and these are the go-to topics normally when anyone thinks of optimizing SQL. So that means people always, they never miss out on these aspects, and there are good amount of methods, but they are still finite methods people can refer to. But today we'll try to look at some other aspect called query level optimization. So this is also equally important, especially when if you're dealing with small amounts of data, this may not be that significant, but when your data set that you're dealing with is larger, then query level optimization becomes very important. Typically this particular area is relatively less focused on whenever SQL optimization is in discussion, but this is the documentation that you find on this particular topic is also very limited on internet reasons, because the level of or type of optimization that you do on query depends on the query that you write. So it varies from one query to another query. It depends upon a lot of factors, depending what kind of data that you are dealing with, what is the logic that you're writing, and what is the complexity of the logic. All of these factors make it unique for each and every case, what kind of optimization techniques that you need to apply there. So because of those things, there are just few points that were documented on this query level optimization, but we'll try to cover some of the important pointers that we can keep in mind whenever we want to look at optimization at a query level. So we'll first go through some of the basic we'll understand what query level optimization is, and also look at some tips to ensure that the query is optimized, whatever the query or the query that we write is optimized. So if you take any SQL client, and the entire process of query from query writing to query output generation is will go through some flowchart like this. There are three main stages to this particular flowchart. So one is called the parser, and then the optimizer, and then the evaluation engine. So once you write a query and hit the run command, so that there comes something called as parser. It will basically check for any syntax errors and all of that sort of stuff. And then there comes a translator. So normally if you see, SQL is very human readable language, right? We write code in almost like plain English sentences. So for it to be understood by the actual SQL engine on the backend, it has to be translated from a high level language to a low level language, which is machine readable. So translator does the job of converting all the code that you have written to something that can be understood by the machine. And then comes the optimizer piece. So this will have the all the information about the tables that you have in a database, not necessarily the data of the tables within the tables, but it will have some metadata about those tables. What kind of fields are there? What kind of data types those fields have? All of those stuff. And it will try to, the main goal or main work of optimizer is to understand the logic that you have written in your query and prepare a most optimized execution plan. What steps I should it should take first, and what step I should take next. So it will try to prepare a optimized sequence of steps to execute your query that you have written. So that is the job of the optimizer. And from optimizers will emit something called as execution plan. So, and that execution plan is taken to the database engine, which will eventually proceed according to that plan and generate the output that you want. So this is how a typical when you write a query and hit a run command, this is the process that happens in the backend. And oftentimes your optimizer is capable of finding the good as it said, like it will give you the right optimized execution plan, but the way there are certain limitations to it. The way we write the query affects the optimal result that the optimizer provides us. So because of that, there are certain pointers that we need to keep in mind while writing the query so that the optimizer can result in maximum benefit. So so we'll look at some of the pointers that we need to keep in mind while writing a SQL query. So first, let me start with the very important one. Actually, let me see. Obviously, query optimization, we need it for a couple of main reasons. One is we want the latency to be reduced. Once you hit the query, whatever the reason, we would obviously want it to be processed as soon as possible. So this is one reason. And lately we have been dealing with systems like Snowflake and all, where all the processing, SQL query processing happens on the cloud. So what does that mean is if your query is let's say very inefficient and highly uses very large amounts of computing powers, then that means you have someone else is lending you those computational resources and that power, so you have to pay them. So more inefficient queries that you have in your system, your costs will keep on adding up, and that's definitely not a good thing. So query optimization will also help you there a little bit in terms of reducing the cost. And the other thing that is normally the query optimization targets is, let's say if you have a number of tables or a number of data resources in your database, your queries should be written in such a way that minimal amount of resources are utilized to get to where you want to be. So this is one another thing, objective that the query optimization normally tries to get it. So so now let's try to look at some of the tips. So we all are aware of joins in SQL. We normally deal with joins everywhere in Tableau and all of those things. And so oftentimes people miss out the fact that if they use joins in wrong way, it can lead up to massive amounts of inefficiency in the query. So this can be explained from various reasons, but one of the popular reasons is about the data cardinality. Whenever we want to join two tables, we have to make sure what is the cardinal relation between those two tables. Is it just a one-on-one relationship between those two tables, or is it one-to-many relationships? If it is one-on-one, the performance may not be impacted that much, but if it is one-to-many, it will be impacted, even some cases exponentially it will degrade based on the number of tables you keep on joining. So let's take a quick scenario and understand how that works. Let's say here we have 4 tables. My table 1 is the base table to which I'm joining all these 3 tables additionally. Okay, and the first row helps me understand like how many rows are there in each of these tables. Okay, let's say my base table has only 1 row, and table 2 has 5, and likewise 3 and 4. Table 3 and 4 also has 5 records. And let's assume I'm just joining each of these tables in a serial basis. Table 1 is joined to table 2, the output is joined to table 3, the output is joined to table 4. So the number of rows that I will get in each of those serial consequent joins is at the bottom. So one row in the table, given that the cardinality is one to many, so one row in table 1 is linked to 5 rows in table 2, and each of those is linked to 5 rows in table 3. So that means we will, the more we go into just joining 3 tables, we are converting one record in the base table to 125 records for the final join output. 125 records may not look that much for a small data sets, but think of a situation like this where your base table has 1 million records, okay, which is something very likely possible. In that case, your joining is resulting in 125 million records, which is almost actual size of an entire database you can think of. So so such joins and the cases that I have considered here are very minimal. So typically in actual reality, the actual cardinality of one to many, if at all there is noticed, it may not be just 5, it can be much higher number as well, 20, 30s as well. And I'm pretty sure that some cases there will be, we may have to join more than 3 or 4 tables. So in that case, this number will just keep on increasing exponentially. So yeah, so you can clearly see that the amount of data that this query has to deal with, and this obviously leads to performance lag. So this is one thing that you have to keep in mind whenever you have to make the joins. Check the cardinality. If it is 1-to-1, you don't have to worry about it. You can join as many tables as you want. So that is number one thing. And the other thing about joins is that so we have just realized seen how a optimizer prepares the optimized execution plan based on the query that you have prepared, right? So what happens, it is normally, it is okay to use as many joins as we want if they are one-on-one, but there is it's also recommended that we don't overuse the number of joins just because they are one-on-one. So we have to limit the number of tables that we can join as well if there is a possibility. The reason for that is, as I said, the optimizer will be affected by the query that we write. So its optimal output will be affected by the query that we write. So the more the tables we join, it has been noticed that the optimizer will tend to slightly the efficiency of the optimized plan that the optimizer outputs will keep on reducing. So you should only be very thorough that if you're joining a table in a query, that you have to then make sure that it is must. So yeah, so those are a couple of points, and the other thing about joins is that something called as CrossJoin or Cartesian join. So it's just that each row of the base table is multiplied with all the rows of the second table that we are doing. If you think about the first point where we are talked about one-to-many relationship, this Cartesian join is even worse form than the one-to-many relationship that which we have talked. There, one record is being only multiplied with whatever the cardinality is. But here in CrossJoin, irrespective of the cardinality, you're joining one record of the base table with all the records of the secondary table that you're joining. So typically this sort of joins are not recommended, and they tend to be performance intensive. So there are ways that we normally do cross join and all, but there are some other ways people don't realize that they are doing cross join without actually using the cross join keywords. So there is a popular example called this particular case on the top. We are not using any joins. We are just calling explicitly in the first query. But what we are doing is just a cross join. So it is just a different representation, but what it is doing in the backend is just doing a cross join. It's taking two tables called P and PC, and we are selecting fields from both the tables. That first it will join both these tables on a row by row level, and then it is filtering the results where this is equal, these two IDs are equal. So this will lead to very inefficient ways. So instead of that, you could just do a simple inner join. That way your cross join is not formed, and you can see a lot of improvements. And one other thing is here to keep in mind. So in the first query, apart from the cross join fault, there is one other thing that we can do to improve the performance a little better. That is, always do filtering before the joining. So if at all that is possible. So here in the first query, if you would see, we have first joined two tables and then filtering the records that we want. But we could have done the opposite, right? So we, if at all there is, if it is possible, here we are doing the same thing. We are joining only on the accounts where they are both equal. So likewise, whenever it is possible, you have to first filter down your individual tables to the level that you want, to the data subset of the data that you want, and then only join those things, so that you will avoid using your computer resources, or you will save some time in processing or joining unnecessary data that you want. So yeah, so this is a little bit on the yes, I think this is I covered. These are a couple of points on the joins, and then there is something called as loops. For those of you who are familiar with SQL, there is something called a concept called loops, and many SQL clients allow to develop for loops or while loops, such sort of programming in SQL. And the reason why we need to avoid loops is that when you pass a query, as we have seen in the first process, there are three main steps. One is the parsing step, one is the optimizing step, and the other is the actual running the code, right? So the entire duration for which the code has taken to run, it can be split up into two times. One is called compile time and one is called actual execution time. So when we do a loop, and within that loop, if you, let's say here we have defined a query and we are putting that same query in a loop of certain iterations, what is happening is we are unnecessarily getting that compile time for the same query which we know it's already compiled again and again. So that will add up to accumulation of unnecessary compilation time, and it will lead to performance degradation again. So, and that is one reason. But typically, even without that, even if your query is not that compilation intensive, then people, even then, they don't recommend it, because the loops by themselves, by nature, they are very inefficient. So they so typically people use loops in various scenarios, but majority of those use cases will be in data insert or data update related aspects. So people, SQL clients these days also offer several features for you to do the bulk updates or bulk inserts or bulk deletes, so without actually going through all the looping mechanism. So these sort of updates are when doing such updates at a bulk are way more efficient when compared to loops. So this is one thing to avoid loops when it comes to performance. And there is one other aspect, important one, is something called as correlated subqueries. So when we write select star and all of those statements, and if you want to create some temporary table, we will write another subquery within a query, right? So often there is no problem as long as that particular subquery doesn't fall into something called as correlated subquery. So here what happens is, there is a table called C, customer C, and we are also using a table called company. So what a correlated subquery means is that there is a parent query that you have written and there is a child query. So here, whatever the query that is in the parenthesis is called child query. And what SQL tends to do when such a parent and child are related in a query, in a single query, is that it will try to run the child query for every row in the parent table. So if your customer table has 1000 rows, it will run this particular subquery 1000 times. And it may work for smaller data sets. You may not see that intensive time being taken, but it's a very inefficient process.